Welcome back, guys, and the subject of this video is going to be section 13.4 from our textbook, which is law of sines. We've done a lot with general trigonometry, sine, cosine, things like that, but today we're going to look at three different applications of the sine function. So this video will kind of be broken into three distinct parts. And so the first part here on the screen is a method to calculate the area of any triangle using the sine function. And you might be thinking, wait, we have a formula to calculate area of a triangle, 1/2 base times height. And that's not wrong, but what it requires is that we have two sides that are perpendicular, that are base and height are always at a 90-degree angle. And so this formula is great for right triangles. However, what if we didn't have a right triangle, such as the one down here in the bottom left of the screen? Well, this is where our new formula will become very useful. So taking a look at the cutout from your book, you'll see three equations down here, all saying area. And if you look closely, they all kind of say the same thing. I usually focus in on this one. So I would write down in your notes that bottom equation. That's the one I'm going to quote. And I think in a second, you'll see why all three of these equations are basically saying the same thing. So the one that I boxed says that the area of any triangle, no matter if it's a right triangle or not, is 1/2 side length A times side length B times sine of angle C. Again, that capital C indicates that it is an angle. So what is this saying? Well, in the picture over here, the diagram, 1/2 times A times B times sine of the angle in between them. 1/2 times two side lengths times sine of the included angle is the official term, but the angle in between them. If we look at the equation right above it, it says, well, area is 1/2 A times C times sine of angle B. Again, that's just two side lengths and the angle, the sine of the angle in between them. So these three equations all say the same thing. The top one, 1/2 times B times C times, you guessed it, sine of angle A, the angle in between them. I like to just memorize and think of that bottom one, 1/2 AB sine C. That's how I learned it, and it keeps those alphabetical values in alphabetical order. So 1/2 AB sine C. And using this, we can find the area of any triangle, which is kind of handy. So just to show an example here, we are given this triangle ABC. We know what angle B is. It's 112 degrees. Side length C, which is across from angle C, and side length A, across from angle A, are given. So we can utilize area equals, in this case, it'll be 1/2 AC times sine of angle B. And I'll write out area so there's no confusion of that being like angle A or anything. Area equals 1/2 AC sine B. Once again, I'm not too concerned about the letters. It's just two sides and sine of the angle in between them. So plugging this in, 1/2 A was 5 feet, C was 6 feet, sine of 112 degrees. And if we look at that now, we could say, 6 times 5 is 30, 1/2 of 30 is 15. We absolutely could do some work, mental math or on paper. But at the end of the day, we're going to be grabbing our calculator and saying, okay, what is 1/2, I'll put it in parentheses, times 5 times 6 times sine of 112 degrees. And let me just make sure really quick, I am in degree mode. Yes, I am. It'll tell me that the area is 13.9078 square feet because it's an area and our measurements were given in feet. And that That looks about right. 5 and 6, if you pretend those were the base and the height, if they had intersected at a 90-degree angle, 1/2 base times height, 1/2 times 30 is 15. So it's a little bit less because this is chopped off. It's not a complete right triangle. This is just a handy way to get the area of any triangle, whether it's a right triangle with a base and height clearly defined or not. 1/2 AB sine C. 1/2 times side times sine of the angle in between. So take just 60 seconds, pause the video, try this one, and my recommendation for you is to draw a picture so that you can see exactly what's going on, where these sides are, where the angle is. I'm gonna pause, I'm gonna get some work on the screen, and then we'll both unpause and check how we're doing. All right, so back to it. I have some minimal work on the screen. You know, I've said, okay, so let's call this B 12 centimeters, and we'll call this C 12 centimeters. So we know it's an isosceles triangle. And mine might be completely not to scale. I don't know if my angle will come out looking like it actually is, but I know that angle B is across from side B, angle C is across from side B, so that means this must be A, so 60 degrees. So the way I drew it is definitely, that angle's too large, but again, it's a sketch just so we can see this. I've got a side, I've got a side, I've got the angle in between. I'm gonna say that area equals 1/2 B C times sine of A. Come over to my calculator. 1/2 B C sine of A. Oops, 60 degrees. And 62 for my area. 62. Okay. Does that seem like a reasonable answer? I'm going to write it down. 62.3538. 62.3538. So again, what would not be a reasonable answer? If we had gotten something like 4, the area of this triangle is clearly not 4 square centimeters. I'll add those units on. If we had gotten something in the millions, that's probably too big. But 62, looking at this triangle, seems about right. It's not drawn to scale. Using our formula, area of this triangle. So this is the first of 3 parts of this lesson. And frankly speaking, I don't want to call any bit of this unimportant, but it's probably the least important. It's a good way to find the area, but law of sines is more commonly used for something much bigger. And that's what we're going to dive into right now. So this right here, if you say law of sines to someone, this is usually what they are going to see in their head and assume you are talking about. And this equation that I just boxed in purple is a big, big deal. Sine of A over A equals sine of B over B equals sine of C over C. Let me talk about what this means. This means that there is a very predictable relationship between how big an angle is and how long the side across from it is. We actually have seen this in geometry. We had a theorem, and it was, I mean, when I teach geometry, this is the phrase I always say. I say, big angles are across from big sides. On that triangle over there to the right, angle C, just by visual inspection, looks like the largest angle. Side length C is the longest side. Big angles are across from big sides. I'll say BABs. And then little angles, angle B looks the smallest, side length B looks the smallest. Little angles are across from little sides. LOLs. BABs and LOLs. So this is what is being formalized by this triple equation here. Sine of A over A is equal to sine of B over B is equal to sine of C over C. There's a relationship. The bigger the angle, the longer the side across from it. So we're going to use that to solve some triangles. And here's the first example. We're given this triangle ABC, and we're asked to solve it, meaning find all missing sides, all missing angles. Now, To find all the missing pieces and to do so using law of sines, we have to have what I'm going to refer to as a perfect pair. For this to work, we need to know both angle A and side length A, or angle B and side length B. We're going to have to, or C and C, we're going to have to know one of these ratios fully, and then part of another one. So right now I have angle A, but I don't know side length. I have angle B, I don't know side length. I don't have angle C, I do know the side length. And what I'm hoping you realize is we can find angle C, because we know that A plus B plus C have to add up to 180. So C is equal to 180 degrees minus A minus B, 180 minus 59 minus 48. And this is just that fairly well-known property of triangles that all their interior angles add up to 180 minus 48. So according to the calculator, to make everything add up to 180 degrees, angle C is 73 degrees. Not too bad, not terrible. You've done that many times before, but now we are in a position to use law of sines. And here's how we're going to do it. We're going to take that triple equation. We're only going to use two parts. So one of the parts is definitely going to be this perfect pair that I just circled in blue, because we know both pieces. I know that sine of 73 degrees over the side length across from it, over 62, has to equal, and then I get to choose one of the other sides that I want to solve. I'll do A first, just because it's the first letter in the alphabet. I'll say sine of 59 degrees over side length A. So I'm only using two parts of that triple equation above at a time, but I'm going to set up this proportion. Sine of 73 degrees over 62 is equal to sine of 59 degrees over A. And then I'm going to cross multiply. So A times sine of 73 degrees is equal to 62 times sine of 59 degrees. To get A by itself, I'm going to divide both sides by sine 75. A equals 62 sine 59 degrees over sine, oh, I didn't divide on this side. I didn't show it anyway. Over sine 75 degrees. And so before I plug this in my calculator, I always like to get a good idea, an estimate, and say, okay, what seems like a reasonable answer based on this picture? We can never really trust a picture to be to scale, but this one looks okay. The 48 looks about 48. The 59 looks about 59. Same with the 73. So if this is 62, I think that side length A looks a little bit less than that. Definitely not like single digits, but should be less than 62. So 62 sine 59 degrees divided by sine 75 degrees. 55, perfect. That sounds great. 55.0191. 55.0191. And I'm going to keep 4 decimals just because it hasn't told us otherwise, and that's kind of our rule of thumb. 55.0191. And now I'm almost there. I've almost got this triangle solved. What do I still have to do? I do still need to find side length B, which just by visual inspection, definitely less than 62. I think less than 55. I feel pretty good about that too, because this will be the smallest angle, so that should be the smallest side. So I'm going to do it again. I'm going to say sine of 73 degrees over 62 is equal to, change colors, sine of 48 degrees over side length B. And then cross multiply. B times sine of 73 degrees equals 62 times sine of 48 degrees divide to get b by itself, divide by sine 73. I will remember to show it on the other side this time. B equals 62 sine 48 degrees over sine 73 degrees. And so again, punching it in my calculator, I don't think I should get a teeny tiny answer, not a single digit answer, but definitely less than 62 sine 48 divided by sine 73. And we'll make sure it looks roughly to scale with the other ones. 48 seems very reasonable. 48.1802. 1002, 1802. $48.1802. And there we are. So this is how we can use law of sines. Okay, this is how we can use law of sines to solve triangles. As long as we have or can find that perfect pair where we know angle A and side length A, or angle B and side length B, or angle C and side length C. We have to have a perfect pair. And then if we have one other piece, we can find the missing piece of another pair. So here's the next one. And this one's a little bit different because instead of starting with two angles and just one side, here we have two sides and one angle. But you'll notice we do have a perfect pair here with side length and angle measurement C. So I'm gonna start by saying sine of 75 degrees over 3 equals, and then what should I do for this next part? I probably need to use that too because that's the only other piece of information I have. Now I'm solving for an angle, so sine of A over 2. Now looking at it, I think it's going to be less than 75 degrees. Big angles, big sides, little angles, little sides. But how does this change the procedure if I'm solving for an angle? Let's check. So 2 sine of 75 degrees is equal to 3 sine of A. I know I need to get A by itself. Step 1, divide by 3. So 2 sine of 75 degrees over 3 equals sine A. And if you think back to earlier in this chapter, you actually do know, how do we get A out of a sine? How do we undo a sine? The answer? Inverse sine. We're going to apply that inverse sine to both sides because inverse sine of sine undo each other, cancel each other out. Now we have inverse sine of 2 sine 75 degrees over 3 equals A. And now the biggest worry I have is just making sure I get my parentheses lined up, that I'm plugging this in my calculator correctly. So inverse sine of, I'm going to put the whole numerator in parentheses just to be safe. 2 sine 75, close the sine, parenthesis, close the numerator, parenthesis, divided by 3. And it says 40 degrees. Does that look reasonable? And again, we usually round degrees to the nearest degree, so that's why I'm not keeping the decimals. I would say, yeah, this is looking 40 degrees, very reasonable. A equals 40 degrees. Now, once I have that, I can find angle B because of the 180 trick. So I'll say 180 minus the 75 for C minus the 40 I just found for A equals B. So B is going to equal 180 minus 75 minus 40, 65. 65 degrees. So I now have all three angles, and all I'm missing is side length B. What I want you to do is try that one, setting up a law of sines problem to find that missing side length B. I'm going to pause it and find it myself, and then unpause and show you my screen, and hopefully we get the same thing. All right, as you can see from my screen, I got 2.8148 for my value of B, which fits perfectly with my big sides across from big angles, little sides across from little angles idea. Work is there on the screen. Hopefully you got something similar. So this was part 2 of this lesson, this video, which is using the law of sines, the one that everyone thinks of when you say that, sine A over A equals sine B over B equals sine C over C, using that to find missing side lengths measurements of a triangle. So we're going to use that to springboard into the third part of this lesson. And it all has to do with this table that's on the screen right now. And so what I want you to know about this table is it's not something you have to memorize. You're going to have it with you. We're going to provide it, and it's one of those things that anyone who needs it, honestly, will just look it up in a book or on Google. But analyzing possible triangles given certain pieces of information. So take a look at the italics here. It says, suppose you are given 2 lowercase letters, so 2 side lengths, A and B, and the angle, capital A, so an angle across from one of those side lengths. Now, there are times that the law of sines is less than specific, okay? And here's what I mean by that. Well, if we type A into a calculator, well, we don't need to type it in, we know A. If we type B sine of A into a calculator and it turns out that it's greater than just A, that means there's no possible triangle that can have these measurements. And I like this picture up here because it's saying B sine A is like the height, if you will, and our A is too small. It can't reach down to the bottom. We know the angle has to be this. We know what this side length is. We know what this side length is. And there's no possible way we can reach down to the bottom. So if A is less than B sine A, there's no solution. And I should have mentioned before, specifically when our angle A is an acute angle. The other half of the table will deal with the other case. But when A is acute, if we type in B sine A and it turns out greater than side length A, no possible solution. If A exactly equals B sine of A, exactly, one solution. One solution because it reaches down and it hits perfectly. It's that height, one solution, and that one's not too bad to solve for. Also, if A is greater than or equal to B, one solution. That means that B sine A is right here, and A is greater than or equal to B, so it has to swing out because that's the only place for it to connect with that bottom side. But the interesting one is right here in the bottom left. If B is greater than A and A is greater than B sine of A, there are actually 2 possible solutions for our triangle. And here's why. Take a look at the diagram on the screen. A is such a side length that it could swing in. It could swing in towards that vertex, that angle A, and it would fit fine. It would be a good triangle. Or it could swing out. And who's to say, based on the information we're given? Not us, we don't know. We have to actually go through and find the 2 possible triangles there. So that is the interesting case when looking and analyzing these possible triangles. On the other side, if A is a right angle or obtuse, more than 90 degrees, if A is less than or equal to B, there's no solution because A just physically cannot reach down to connect the triangle, so there's no way that can happen. If A is greater than B, one solution, okay? And this actually makes a lot of sense because if A is right or obtuse, then it will be the largest angle since they all have to add up to 180, which means there's no way B can be a bigger side length. Small side, small angles, big sides, big angles. So we're going to run through just 3 examples of using this table, using this chart to figure out how many possible triangles are there and solving for possible triangles. So right here, determine whether each triangle has no solution, one solution, or 2 solutions, then solve each triangle. Round measures of sides to the nearest 10th and angles to the nearest degree. Got it. So in this first one, angle A is 99 degrees. That tells me I'm looking over here because A is an obtuse angle. We're told A is 2.5, B is 1.5. So clearly, A is greater than B. One solution, one possible solution. So there's one solution to this triangle, and how do I find it? Using law of sines. I'm going to say that this is 99 degrees. I tried to draw it a little bit more than a right angle. So that's angle A, which means side length A is across from it, 2.5. I'm going to call B this one. I don't know if that's going to be to scale. And I don't know what C is. So I need to solve the triangle again. But look, notice we have a perfect pair. And so I can set it up and go sine 99 degrees over 2.5 is equal to, I'll do sine of angle B over 1.5. What I would like you to do, because we've already done a couple of these, pause the video, work it out, solve this triangle. Now that we know there's one solution, it's just like any other law of sines problem. So pause your video, work it out, then check your answers with mine. All right, my finished work for this problem is on the screen. I got that angle B was 36 degrees in green using law of sines. Then I used purple even more to the left to find angle C, making sure they all add up to 180. And then side length C 1.8 based on another law of sines. So hopefully if your answers matched mine, then we're in good shape on this problem. If not, pause it, look at my work, look at your work, compare, where does it look different? See if you made a mistake, see if I made a mistake. If I did, please let me know. But if we look at the table and we see there's one possible solution, one possible triangle, it's just like a normal law of sines problem, okay? Let's look at the second one. Same instructions. A equals 124 degrees. So once again, that puts us squarely on this side of the table because A is obtuse. A is 1, B is 2. A is less than or equal to B. That means there's no solution. That means there's no possible way this could happen because look, B is a bigger side. B would have to be a bigger angle, but how are we going to get a bigger angle than 124 and still fit in our 180 degrees for a triangle? So these are actually kind of a gift if you get one like this, because all you have to do is say no solution and you're done. So only one more problem to go, but you might be able to predict what's going to happen. Same instructions. A is 80 degrees. So it's an acute angle. I know I'm not using that right-hand side. So that means I need to figure out what this B times sine of A is. So I'm going to come over here to my calculator. I'm going to say, what is 9.1 sine of 80 degrees? I'm just going to record that B times sine of A equals 8.9618. Is A less than B sine A? No. Is A equal to B sine A? Close, but no. Is B greater than A? Yes, 9.1 is greater than 9. And is A greater than B sine of A? Yes. Here is our example with two solutions, and I'm going to show you how we handle that. It has to do with that side swinging in or swinging out. And so what I'm going to do is I'm going to start this off kind of a similar way. I'm going to start with a law of sines because I know that sine of 80 degrees over 9 must equal sine of B over 9.1. Let's cross multiply. So 9.1 sine of 80 degrees is equal to 9 sine of angle B. Divide by 9 on both sides. So 9.1 sine 80 divided by 9 is equal to sine B. I'm going to need to inverse sine both sides. And here's where the trick kind of comes in. I want to say trick. I don't mean like a trick question, but this is the key point to understanding how there could be two solutions. I know that I need to inverse sine both sides specifically so that on the right, my sine disappears. So as I'm writing this down, what I want you to think about is, what is inverse sine doing? Think back all the way to 13.1. When we said inverse sine is telling us what angle has this sine value. What angle has this sine value? And we've seen on the unit circle that the sine value is actually just the y value. Sine equals the y, because y over r, but r is 1 in the unit circle. So sine is just the y. So inverse sine saying what angle has this sine value is saying what angle has this y value. And so I'm going to type in inverse sine 9.1 sine 80 divided by 9. 85 degrees, right? 85 if we round to the nearest one. And so it says 85 degrees is the angle that has our desired y value. And I'm going to say it's right about there, 85. Which looks good. I like it a lot. But there's another point on this circle that also has that exact same y value. If you look, there's a point over here in quadrant 2 that will have that exact same y value. That could have been an answer to this inverse sine were our calculator programmed to give it to us. So how do we figure out what that is? By using our knowledge of the unit circle. You know, we're saying that this, if I zoom in, is 5 degrees. Because 85 is 5 degrees from 90. Well, then guess where we have to go to get the other angle that has that same y value? 5 degrees the other way from 90. What this is telling us is that B could be 85 degrees or it could be 95 degrees. Both of those have the same y value, they have the same sine value, and so both of them would work in this case. So we're going to get an answer, and I'm going to try to draw a line there, because our answer is going to consist of two possible triangles. Let's start with the first one. The first one was B is 85 degrees. So that means minus 85 equals 95 degrees, and then subtract our 80 degrees. Because the triangle needs to add up to 180 degrees, if B is 85 degrees, C has to be 15 degrees so that it all adds up to 180. But what if B was 95 degrees? Subtract that 95 out and subtract the 80 out, and we're left with C is 5 degrees. So again, this is alternate reality. On top, if B is 85 degrees, then C is 15. But on bottom, if B actually was 95 degrees because it swung out instead of swung in, C would be 5 degrees. Finally, to find side length C, we're just going to do our law of sines. Sine of 80 degrees over 9, that's what we started with, equals sine of 15 degrees over C. Side length C is what I'm solving for. And I will try to keep all my work above the line. So I'm going to zoom in so I can write smaller. C sine of 80 degrees equals 9 sine of 15 degrees. Divide by sine 80. C equals 9 sine 15 divided by sine 80. And we're told that 2.4 if we round to the nearest tenth. C would be 2.4 in this case. So alternate realities, top, because there are two possible triangles. On top, B is 85 degrees, C is 15 degrees, and side length C is 2.4. What about that other possibility though? We'll do the exact same thing, except using our C value of 5 degrees. That is our bottom alternate reality. So C sine of 80 degrees is equal to 9 sine of 5 degrees, divide by sine 80. And so we get C equals 9 sine 5 over sine 80, 0.8. So these are our two possible triangles. I'm zooming way out. Our two possible triangles because we looked at the chart and it told us there are two possible triangles. So how did we go about this? We did in red our first law of sines, our normal sine A over A equals sine B over B. But when we got to that last step, when we did this inverse sine to find our first missing angle, our B, we have to recognize, yes, the calculator tells us 85 degrees will get us the sine value, the Y value we need, but it's up to us to say, hey, 5 degrees this way from 90 has that Y value, 5 degrees that way will have that same Y value. And so that's where we get our two cases, 85 degrees or 95 degrees. And then we go from there on those two paths to figure out what are the rest of those missing measurements in those two possible triangles. This right here, this example, I think this is as hard as it gets. Definitely for this section conceptually, and maybe for chapter 13 as a whole. But if you need to, listen back to my explanation, rewind, work this problem again. Ask me when you see me next, because I would love to talk about this. I anticipate the need to. I expect this to be kind of a hard thing to grasp because it's a very hard thing to grasp. It's very abstract. But these are the three parts of law of sines. We started with that formula that we could just use to find an angle, or excuse me, find the area of a triangle. Then we looked at the law of sines, sine A over A, sine B over B, sine C over C, which allows us to solve triangles if we're missing sides, if we're missing angles. So we got lots of practice with that. And then we had three examples about analyzing possible triangles, saying, using this chart, is there one solution, in which case it's a normal law of sines, zero solutions, in which case it's lovely, no solution, or two solutions, which is that harder conceptually, that harder scenario that we just demoed. So take a look at your practice problems. Ask me all the questions you have when you next see me. I'm hoping this was helpful. This was law of sines, and in the next video, we're going to look at law of cosines. Until then.